Morning to all. I, Priya Dhuria, PhD Research Scholar of Department of Physics, MRSPTU, Batita. Welcome you all for the start of ATAL online FDP on topic novel materials and their application. Session 1 of the first day of FDP is being addressed by Dr. Ravi Kumar, Professor, Department of Material Science and Engineering, NIT Hamirpur. Dr. Ravi Kumar is working as a professor and head Department of Material Science and Engineering, NIT Hamirpur. He has obtained PhD degree from Tata Institute of Fundamental Research, Mumbai in 1994. He has also held various administrative positions as Group in Charge Material Science, IUAC New Delhi, Head Department of Material Science Engineering, Hamirpur, Principal Byanth College of Engineering and Technology, Gurdaspur, Visitors Nominee for Central Universities, EC Member, Central University of HP, Member BUG PTU Jalandhar. Dr. Ravi has also wide experience of research in the expertise field. He has guided 24 PhD research scholar and 4 are ongoing. He has more than 350 research publications in peer-reviewed index journals, SCI and Scopus, and 9 articles in edited books. He has given and delivered more than 150 expertise talks in international national conferences and symposia. His area of expertise is functional oxide material, electronic structure of strongly correlated oxide materials. In this session, our expert, Dr. Ravi Kumar, is going to share and guide us through the expertise topic of nanomaterials. So I now request Dr. Ravi Kumar, Professor, NIT Hamirpur, to start the today's proceeding and increase our knowledge through sharing. Dr. Ravi Kumar.
Okay. Thank you very much for a nice introduction. And I am very thankful to the organizers who has given me an opportunity to share our recent excitements in the area of material science and condensed matter physics to discuss with you. And today I will talk about the nano materials and nanotechnology for the application of electronics. Let me share my presentation. Host this is not allowed me to share screen. Hello. Host has disabled participant screen sharing. Please allow me to share my screen.
Yeah, permitted, sir. So please try to share your screen once again.
Okay, let me do. Now it's okay. So today I will discuss about the nanomaterials for application in electronics. As Professor Ravindranath ji has explained that the technology and miniaturization of the devices is very, very important. So in light of that, the nanoscience and nanotechnology has been developed. And nowadays, most of the work is going in this direction, how we can prepare the nanomaterials, how we can generate the nanostructures, and how we can add the functionalities in those kind of material for a novel applications of these novel material. So today, I will divide my talk in 2 parts. First part, the fabrication of the nanostructure using ion beams. And second part will be the fabrication of nanostructure or nanomaterials using the chemical routes. So in these two parts, first part I will explain few of the structure, how we can create a nanostructure embedded inside the host matrix, and you can create the nanostructure over a surface by using ion implantation as well as ion radiation. The second part, I will go to the P-type transparent conducting oxide materials and how we can synthesize them first as a single phase transparent conducting oxide materials and then translating them into the thin film for the device point of view, which are as a transparent conducting oxide devices. We can use those kind of material. These are the two parts, because when I first I thought I will give only one part. When I came to know the talk is of 2 hours, so I have decided I can give a 2 part of that. Now, the formation of nanostructure using energetic ion beam, we start with this. This type of work we did at Inter-University Accelerator Center, which can provide the ion beams from low energy to very high energy. Basically, we require a low energy for the ion implantation, like in a few kilo electron volt energy of the ions of various kinds using ECR sources. And second, we use a pelletron accelerator to accelerate the ion of a very high energy up to millions electron volt energy of all kind of ions. And those ions, how we can modify, how can generate the structure. First part, how we can embed the nano material inside the system. This is the pelletron where we used to do ion beam irradiations. And the plan, first part, the plan is of the experiment we are deciding. So let us talk about that. Ion implantation and irradiation is a non-equilibrium process. And using those kind of non-equilibrium process, we can formulate or form a novel phases, metastable structure, induce strain in the host, and precipitate the implanted materials inside the embedded inside the material. This non-equilibrium process will lead me, in general, when we are synthesizing a material, we require the solubility of one material into another. Now here we are using a non-equilibrium process, which is a robust material process. By brute force, we can, irrespective of the solubility of the materials, we can generate those kind of systems. Then, what are the application of that? We can create a devices like optical waveguide, nonlinear optics, magneto-optical optic devices, magnetic memories, photonic devices. All these kind of devices we can make using the ion beam implantation as well as irradiation. I will show you some of the things we have. I am going to demonstrate in this present talk. These features of ion implantation motivates us to formulate the experiments. The formation of magnetic nanoclusters embedded in host matrix, and their structure or phases are controlled by the microstructure of the host matrix. then we can grow the nano pillars of thin film using high energy heavy ion. These two problems we have formulated, and those problems I am going to demonstrate in front of you what we have done in our own hand, in our own lab, not from the interface or internet things. Most of time people are download something and presenting what others are doing. So my basic aim is that only show what we can do within a country and what we can present in our lab, and how our student can also, or our faculty members can also perform those kind of experiments by going to visiting to that places, using those kind of facilities, which we have. I have a major person to develop those at Inter University Accelerator Center, New Delhi. I spent 13 years of my life there to develop that kind of things. Now, first part is the formation of, yes, somebody raised hand, Rahul Kumar. Any question, any problem? No. Okay. So in a host matrix, so we can select our host matrix is a main aim to present the growth of a magnetic cluster and the dependence on the microstructure. So we take a host matrix as a sphere and a quartz, and you see sphere has different phases: alpha phase of Al2O3 and gamma phase of Al2O3. Al2O3, somebody is raising a hand from a participant. Is he want to ask any question?
There is Mr. Rahul.
Yeah, he want to ask something, or because he is disturbing me in between raising his hand. If he has a specific question, I can answer him his question right now.
Mr. Rahul, if you have any question, you may ask to our esteemed speaker. Otherwise, please raise down your hand.
In this process is used to make chips, sir, semiconductor chips.
Gentlemen, let me complete my presentation. Then you can ask the questions in between. Right now, just now I am giving an introduction to the things. Okay.
Okay, sir. Okay.
Keep quiet now. So we are talking about, there are two different phases of aluminum oxide, like closed packed oxygen, like alpha phase, plane arranged in a pseudo hexagonal stacking, AB, AB, etc. And each aluminum atom is located in an octahedral intersite and linked to 3 oxygen atoms in each of the neighboring planes. Gamma Al2 is a pseudo-cubic spinel structure. So now, if we can have to grow the different kind of embedded nanostructure, whether it is the microstructure of my sphere, same sphere is alpha phase or gamma phase, depending upon the initial stage of my host matrix, I can grow that kind of phase of the embedded structure, the aim of this. Then quartz is having a cubic structure. Basically, it's a silicon dioxide. It can again have a amorphous structure also, that is, we call that as the glass and quartz. So depending upon its microstructure, we can grow the oriented nanostructure, or we can grow a isotropic nanostructure, or unoriented or randomly distributed systems. So there are various aims are there. Here we are using both quartz and silica glass as my host matrix, and we are embedding the magnetic ions like iron, nickel, cobalt, and their energy depending upon how deep we want to embed inside the surface. Depending upon the energy of the implanted ion, we decide whether we want close to the surface or in deeper inside the surface where we want to implant the nanostructures. So that's why we have varied the energy from 100 kV to 400 kV. And then the condition is that you can do the implantation at low temperature. You can do the implantation at room temperature, or you can do the implantation at high temperature. Why we change the temperature? Because the microstructure of the host will depend upon the temperature of my experiment. These target will be annealed under different conditions. Starting after implantation, you can anneal it because you want to release the stresses generated during the implantation in the host matrix. Then once we do this experiment, now we want to know that after doing this experiment, can we what we have achieved? What was our goal? Is that goal is achieved or not? So we have to characterize our materials using various kind of characterization technique like X-ray diffraction to see the structure of the embedded nanostructure, atomic force microscopy to see the morphology of the embedded nanostructure, and ferromagnetic resonance, whether they are magnetic or not, or MFM, magnetic force microscopy, to understand the contrast of those kind of techniques. Now, there may be possibility that while embedding, we want to have a pure iron, nickel, and cobalt metal also embedded into the structure and nanostructure in that. Is they are really a metallic or they are having a some kind of oxide formation. I will demonstrate here the examples of few of them here. So these are the experiment. First experiment we did with the silicon dioxide quartz matrix with different doses of implantation, like starting from 5 into 10 to the power 15 ion implanted per centimeter square to 2 into 10 to the power 17 or 16 ions per centimeter square. We can do that. And after implantation, we anneal the sample at 600 degrees Celsius, and then we can characterize them. First experiment we want to do whether they are, what is their structure. So you see the X-ray diffraction peaks, which is clearly indicating the nickel X-ray, and they are indexed and they are matched with the nickel structure, pure metallic nickel structure, and they are having a 111 peaks of those kind of things. Second experiment we did the atomic force microscopy, which is clearly telling, because it is very close to the surface, 100 kV energy, it is below just below the surface, so you can see those kind of structure through atomic force microscopy, and they are showing very nice spherical shape nanostructure of nickel metal present into the system. Then magnetic force microscopy, you can clearly see the magnetic force, the contrast, magnetic contrast is giving you the isolated magnetic domain structure of these are present in a MFM, magnetic force microscopy system. Now, if they are magnetic, then we use squid magnetometer measurement for these. So we have to measure the zero field cooled and field cooled magnetization. Now we know that depending upon the size of the nanoclusters, there is a blocking temperature. Blocking temperature means that below that temperature they are magnetically ordered, and above that they are having a super paramagnetic behavior. So you can see, if you have a narrow distribution of particle size, so you will see a very sharp peak in ZFC at the blocking temperature. So that is clearly indicating they are magnetic. Now, if these particles are, or these magnetic structures are very close to each other, then this peak becomes broad. Due to the reason for this, the dipole-dipole interactions are participating in these kind of materials. Now, if they are having a metallic nanoparticles, so using a UV visible absorption spectroscopy, you can observe the surface plasmon resonance of those materials. So because in oxide material, you can't see the surface plasmon resonance, only the plasmons will exist in the metallic material, whether it's a gold, metals, or silver metal, or nickel metal, or on any kind of metallic system. And if you reduce the size using the Me theory, you can have a surface plasmon resonance in a system. So that is clearly indicating. Now question is this: we are again testing these materials using a X-ray absorption spectroscopy to understand, is that nanoparticles are interacting with the surrounding oxygen or not. If they are interacting with the surrounding oxygen to form oxides, so then there is a multiple structure will be forming, which you can see in elemental specific technique like X-ray absorption spectroscopy using synchrotron. Here we have seen that we didn't see any kind of nickel oxide structures are present. Then we go to the nickel elemental specific, whether they are having a nickel oxide structure or they are having a nickel metal structure. If there is a nickel oxide structure, there is the d orbitals will split up with the oxygen interaction, and these crystal field splitting will take place and give you the multiplet structure. Here we have not seen a multiplet structure. You can clearly see these kind of single L3 and L2 edges of that. Again, if you do this thing in a sapphire, and in case of a sapphire, first we did the experiment with the quartz. Now we have done the experiment with the sapphire. You see, we have measured the nickel 1,1 structure present into the system using high resolution X-ray diffraction. Same, they are showing a magnetism, and then at a 10 Kelvin as well as a 300 Kelvin. And there is a AFM structures are also present into the system in the inside of that. Now, when this is a magnetic, now again using the X-ray XMCD, X-ray circular diachromagnetism technique, basically we are having a right-handedly polarized X-ray and left-handedly polarized X-ray. The interaction of both the polarization of the X-ray will interact with the spin states of these kind of material. Now the difference in that will give you the magnetic moment of that system. Now we have clearly did this, and we have seen that how they are showing the magnetic moment in a nickel embedded structure. Now considering that we have again formulate the magnetization curve using the XNCD signal. And this signal is clearly matching with the signal obtained by the squid magnet. So that's why I have demonstrated we can embed that. And there, these kind of magnetic nanostructure embedded into the system, they have many applications. They can use as a memory devices. They can use as a single electron transport system also. So those I will not discuss here because those are a little bit different kind of arena in the present case. Now I go to the evolution of nano pillars, magnetic nano and micro pillars using high energy heavy. So there we are using a 200 million electron volt energy. How we are doing these kind of experiments? Basically, this experiment I am demonstrating in a very simple materials like a ferrite thin film. So you take a ferrite, magnesium, manganese ferrite thin film deposited on a silicon. You can use a PLD technique, you can use a sputtering technique. Any kind of technique can be used to develop those kind of nano thin films of these materials. Now we want to convert this thin film into the nanostructure. Same, this is the magnetic material. Now if you take a SNO2 tin oxide, this is a non-magnetic material, and now try to grow. It is not that you can do with a one system and you can do that. So that's why we taken a two extreme examples of the material. So two extreme examples of the material, and one is the tin oxide, another is a magnetic material like ferrite materials. Now let us see how you can generate the nanostructure in that. Here, that physics is very simple. What is that? You can deposit energy, very large energy, in very short time at a local position. So what will happen? You can create the excitation of the solid, and then there is a rapid quench. If you melt the system and quench it fast, what you are doing? You have a high temperature and high pressure. So if you generate that high temperature and high pressure in a system, you can create the structural instability, which will grow like this. Why they will grow like a nano pillar? They can grow like amorphous material, they can melt it, they can create another kind of phases. Why? They will, under which condition? They will grow in the nanostructure of the system. That is the interesting part in this experiment. Now, you have created a structural instability. How you can create? You can imbalance created by radiation. Then there is a dewetting of thin oxide film under Chi bombardment can occur, which imbalance the existing inversion system, and then the thin film self-assemble under the Chi radiation stress to give rise to these. See, this is the philosophy, which is a very vague thing. Now see how it will look. Let us say you have a homogeneous coherent film which does not like its substrate. While growing the film, either you put some interface layer of some thin metal, or you select your substrate in such a way that the lattice should not match with each other. Basically, the material like ferrite and silicon, they don't like, the structure is not matching. So they don't like the structure. And if such kind of situation at the interface, what will happen? There will be a positive surface interface energy. And if that kind of a situation, while will form isolated pattern as soon as its atom become mobile. Now, if you create the local heating to the system, the atom will become mobiles, and then the pressure will be generated at the local site and the capillary action will take place. So this is all due to the surface tension science, surface science. So given by capillary force, the imbalance of surface and interface energy will bring them out. So that kind of things can be done by thermally activated. You can do with a furnace with fast quenching. You can do with a pulse laser with a high energy laser beam, or you can do with a ion radiation. So these are three routes. So we use the ion radiation in the present case. Now see, if we do that, what we will get? Do we really formulate those kind of structure or not? Let us see. When you do this first experiment, the first hand characterization, we tell the student or ourselves or our scientist, so do the X-ray diffraction to the system. You see the X-ray diffraction pattern. Even though we have bombarded with a very high energy silver ion of 200 MeV with such a large fluence, the structure does not change. What was the thing? People are expecting that in normal situation, they will get amorphized. There will be structural transformation. And when you have to play with the interface energy and generated the capillary action by designing your system in such a way, then your structure will not change. It means that our first purpose is solved. We have not disturbed the material structure. Then, kuch hua bhi hai ki nahi hai, anything happened or not, that we have to look at this matter. Now you see, atomic force microscopy, there is a smooth film when there is no irradiation. When you irradiate, you start growing these kind of structures. And as 10 to 12, you have very well isolated nanostructure formulated on the surface of a film. These nanostructure look like a nano pillar, or their shape is like the nano, like shivlings. And I call them as a nano shivling or magnetic shivlings nanostructure we have produced. Why I call shivlings? Because it's a source of energy. Same way, these magnetic nanoparticles or nanostructures are the source of energy like Shiva. So we have generated the Shiva energy in the laboratory and making these kind of nanostructures. So they are showing very nicely magnetic structures. Then same experiment we repeated with the tin oxide, and I will show you there again we have produced this kind. And we know that the tin oxide is a very good gas sensor. So if you have a nanostructure, you should enhance the gas sensing property of that. So we have proved that how the sensitivity of the gas sensing is increased when they formulated with the your ion beam. So this is the demonstration for growth of the nanostructure on a surface using high energy heavy ion, and the embedded nanostructure using the low energy, which can be easily used for a device purposes. And this technology and this science we have developed in our own, and now these many people are using those kind of technology in all over the world. So now, before I will go to the second part of my talk, any question, any doubt, please let me know. Otherwise, I'm shifting to the second part of transparent conducting oxide. So Mr. Rahul was asking something. If he has his question now, I can try to answer if I can. No question?
No, sir.
Hello?
Sir, hello, sir.
So shall I continue?
Yes, sir. You can continue.
Okay. Okay.
Continue.
Okay. Okay. Now, the second part of my talk is again another kind of novel materials and their applications. That is the transparent conducting oxide materials. And these transparent conducting oxide materials, basically we have a transparent materials. To transparency of a material, we need a very large band gap. So all the visible light can transmit through that. And for the conduction, we need some kind of impurity states in between the gap. So you have to dope some kind of a material. You are maintaining the gap as well as doping a material. So we can use two types of dopant. One is, we call that as a donors, which lead to the N type of material. And donors are a very close impurity level to the conduction band. And then if you want to convert them into P type, then you have to dope the acceptor close to the valence. Now, these doping we can produce N type and P type. And in transparent conducting oxide materials, the N type production of the material is very easy, and many materials with good conductivity and good transparencies are available. But the P type transparent conducting oxide, first of all, they are very less in number. Secondly, their conduction is very poor. And if you improve the conduction, the transparency is very poor. So that was the problem in front of the whole society, how we can have P type as well as N type of transparent conducting oxide. Same thing when after finishing my term as a principal Beyond College, when I joined back to my lab again and leaving administration, entering into the research in this inning, we thought that let us do this problem, whether we will get success or not. And I started this work with my colleague, Dr. Vikram Verma, and one of my PhD student who has just submitted, waiting for his Viva, Mr. Jarnail Singh, would be doctor very soon. So we started this. So now let us see, transparent conducting oxides have become a leading candidate for invisible electrons, as they exhibit high transparency and high conductivity in a single material. So we call them as a transparent conducting materials. And they're oxide in nature, that's why it's called transparent conducting oxide materials. So if you go back to the history, it is not the new research. Oh, very long back in 1907, beginning of the 20th century, the material known as cadmium oxide was published having a transparency and conductivity in this. And then at that time, nobody was bothering about that kind of, there are so many another issue of science was running at the time. This research was put aside. Later on, people has made many material which are well known as transparent conducting oxide material, like tin oxide, antimony coated tin oxide, zinc oxide, indium oxide, cadmium tin oxide. All these kind of materials were developed. The beauty is that all are N-type transparent conducting oxide materials. So we are not having. Now, why we need a transparent conducting oxide material? If you look at the full application panel, like flat panel display, LCDs we are using nowadays, LEDs, solar cell, invisible security circuits, smart window, touch screen. Nowadays, most of the application we are even using, even my laptop is having now touch screen and all these kind of things. My mobiles are like this. So those touch screen, flat LCDs, flat panel display, solar cell, these applications require a transparent conducting coating on the device. Why transparent conducting? Because the light which should fall, it not be obstructed by the connections or connects. First application was to make a transparent connects and anti-reflection of that. So that's one purpose. Now, if I want to go for the electronics application, so I have to go for N and P type both, because we know that if I want to make a even diode, pin diode, or those kind of devices or transistors, I need both type of semiconductor materials. Both type of conduction should be there. Either it should be a P as well as N. And we have very available material, but the P type oxides are generally less conductive and less transparent. So many efforts are going on. Hello? Many efforts are going on in this direction. So nature of the band structure limits the potentials of most common oxides. Who limit these P-type TCUs? That is the band structure. Why? Because when you have oxide materials, the oxygen 2p orbital of valence band in most of the oxides make those bands very flat and leads to large hole effective mass. What I mean by that? Basically, they will localize these 2p orbitals of oxygen in the oxide material, will localize the hole and restrict their motion. Basically, the velocity will be reduced. Basically, if you plot the EK diagram, energy into momentum diagram, they will be very flat. The flat mean as the parabola becoming flat, the effective hole mass is increasing. So if the whole mass is increasing, it is having a restriction to drift to be conductive into the system. Now, if a positive hole is introduced, by a substitutional doping that may localize on a single oxygen atom and cannot drift with the crystal lattice even in applied electric field. That is the basic fundamental of chemistry and physics you can understand. Now, how to overcome? So lack of highly effective p-type transparent semiconductor as compared to n-type counterpart required a lot of research in this. So we have to devise the way how we can do that. As a finding better p-type TCO, one would extend the application of TCO as a transparent electronics, facilitating the fabrication of p-n junction to pave the way of transparent electronics. p-n junction could lead to a functional window which transmit visible portion of solar radiation, jet generates electricity, and by absorption of UV. Transparent diode which rectifying behavior can be fabricated. UV emission from diode by current injection to the p-n junction, heterojunction at room temperature has been already some reports are there, but only on the laboratory. And if you look at the literature and you start some kind of a research, you start searching कि भाई किसी ने कुछ किया और थोड़ा रास्ता मिले, so you can get some lead to that. And when you go to the literature, we go back in 1993. Sato was a scientist, Japanese scientist, who make a nickel oxide. They observed about 40% transmittance of nickel oxide film in visible region, and when they fabricate its spin diode like p-type nickel oxide, insulating nickel oxide, insulating zinc oxide, n-type zinc oxide, and they found that the transparency reduced to the 20%. But this is not good for the application, and but it has given us a lead. Okay, it can be improved. Now, how to improve it? Improving this, again, the solution was provided by a theoretician, that is Kawajoe, again a Japanese theoretician. Conductivity is to modify the valence. How to increase? You have to modify the valence band edge. How you can do? Excuse me. Hello. नमस्ते जी, मेरा ना बेटा लेक्चर चल रहा है, बाद में बात करते हैं. So you have to modify the valence band by mixing orbital of appropriate countercation that can fill energy field levels comparable with the 2p level. Basically, what is that? That is nothing. It's a chemical modulation of the valence band. So that is the procedure. If we can chemically modulate the valence band by using the countercations in such a way that we can improve this. Then we go by a literature. The first p-type TCO material was copper aluminium oxide, was reported in 1997, which can maintain the transparency of 60 to 70%, and conductivity is again a very poor conductivity, 1 Siemens per centimeter. Now, question comes to the picture that how we can okay, so how we can proceed. So at that time, because I am a person from a magnetism, started working in semiconducting system in spintronics, then in multiphoroic. Now I jumped into this. So I thought, let us start with some material which is chromium oxide. Why? Because it's having a large band gap. So 3 electron volt and above. And it is an insulator. So I can introduce the conductivity into that. And it is anti-ferromagnetic. If I, while doing some playing with the modulation of my valence band, I may generate some magnetism also in that. So I opened the window while thinking to this problem. So I selected this material. And you look at its structure, it's having a corundum structure with hexagonal closed packed layer of oxygen atom, and 2/3 of the octahedral sites filled with the chromium atom, and its primitive cell is a rhombohedral with crystal parameter K is equal to 4.959 angstrom, and C axis is very large. So now, how to increase its conductivity? So various efforts were being made using lithium, calcium, indium, zinc, all those kind of things. But some of them are not giving any conductivity, or they are leading to insulator, or they are of N type, or their conductivity is very, very less. So then we thought, we have our main aim is to chemically modulate the valence. Now my countercation should be interacting and taking place of the chromium atom into the structure. So which kind of substitution atom I have to select? So that is the real problem. So we thought we can take magnesium, aluminium, and nickel. Why magnesium? Why aluminium? Why nickel? First hand thing is that their ionic radii should be comparable with the cation which you have to replace. Then second is what is their electronic structure? Now magnesium is a non-magnetic, so there is no magnetic localization problem. Now they can easily go inside the Cr2O3. Aluminium is again a non-magnetic. Magnesium is a divalent. Aluminium is a trivalent. So I can have a charge compensation in that. Charge disproportionation, so which can lead to the hole into the system. And nickel, because it's again an ionic radii is comparable, but it has a d electron. Now when the d electrons are there, and it can either be in a +2 state or in a +3 state. Both the states can be possible, which can driven by. Now we can add a hole as well as a spin to the system. So let us take the things together and do this experiment. So friends, first of all, how we can prepare the nanomaterial? The synthesization is a very simple way. You can use the wet chemical co-precipitation method, simple, using 2 beakers and some flask in your laboratory. You take a starting material as a chromium chloride, chromium nitrate, or chromium acetate. Same way, nitrate chloride or acetate of these transition metals. Why? They can easily dissolve in the water. So I want to have a clear-cut solution of all the three components. Now, depending upon the stoichiometry, and we use a volume of that, because we prepare the molar solution of that, so then we can use the volume percentage of that, how much we have to add. So then once you measure the pH, they are acidic in nature. pH is very low. Now you have to precipitate them using a ammonium hydroxide solution, drop-wise drop, by controlling the temperature and pH value. So at a given pH value, you can see you have precipitate. Now you have to wash them, you have to clean them, you have to separate out them, and then finally you have to dry. And after drying that, you want to characterize them, whether this material is a single phase, what is its transparency, what is its molecular structure. So how you can do? You can do by X-ray diffraction, Raman spectroscopy, UV visible absorption spectroscopy, IR. And finally, once you characterize them, our basic aim is not a powder. We want to make a device out of that. So you have to grow a thin film using pulse laser deposition or RF magnetron sputtering. So we selected the pulse laser deposition because it is in our lab. So whatever is available with somebody, they can do that. So then we try to characterize them. First characterization is X-ray diffraction. Again, X-ray diffraction for a magnesium doped system, magnesium substituted system, up to 50 X is equal to 0.5 in this structure, like 25% of that doping is there. All the materials are single phase, no structural change there. And they are very nicely X-ray diffraction analyzed by Rate-Wild analysis, and we see how, and then we can find out the lattice parameter value, then chromium oxygen bond length, bond angle, everything we can analyze using a Rate-Wild analysis, and then we can find out their size using Scherrer relation, and we can calculate the strain in the system. So those parameters we can do. First, the lattice parameter, as we are doping the magnesium, the lattice parameters are decreasing. Both A and C, both are decreasing. And in a low concentration, like up to 0.05x, or at high concentration range, if they are going in a similar fashion. Then if you see, the crystal size is decreasing with the substitution and the strain is increasing, because as the particle size is decreasing, the surface stress or surface strains are increasing. This is experimental data extracted from the X-ray diffraction technique. And if you have to go with the molecular structure of that, and you see the micro Raman experiment, Raman spectra of Princeton and dopes there, and we have seen that the most intense peak, 534 centimeter inverse, attributed to A1G symmetry, has been shifted towards lower wavelength. Shifting of this peak is due to the lattice strain induced by magnesium substitution, which we have seen through the X-ray also. Then UV visible spectroscopy. Now, UV visible spectroscopy, again, I am telling on the chemistry people are somehow doing better than analysis than physics people, because physics people are only bothering about the top plot, band to band transition. But I will tell you the electronic structure of the electronic transition, because when you have a octahedral symmetry and there is a crystal field splitting is taking place of the d orbitals, and that transition is also lying in a UV visible electronic transition. So here you see there are different kind of electronic transitions are there. Okay, so there is a broad peaks at 640, 460 and 600 nanometer show intrinsic DD transition of chromium ion, and two weak shoulder were observed at 670 and 710 nanometer, corresponding to the spin forbidden transition are also present here. So these are present. Apart from that, there is a band-to-band transition. Now, this band-to-band transition you can see using again a top plot, and from that you can find out the band gap, whether it's a direct band gap or indirect band gap, depending upon the exponent n. So now we have extracted that the band-to-band transitions are giving a band gap. The band gap is decreasing as these states are populating inside the system. So you have change in a band gap. Now similar experiment we can do with the aluminium also. Aluminium is also showing a single phase, and then lattice parameter are decreasing. Then there is again a strain in that in a Raman, again the band gap is decreasing with the aluminium also. This is a powder. So far all these measurements are powder. Now you come to the nickel. Nickel is playing a different role. Here we learned a lot in this experiment. First, when we have a low concentration, 0.05x, they all are showing a single phase. As soon as go to 10% and above, there is a mixed phase. So you have a phase 1, which is a rhombohedral phase. Phase 2, which is a spinel phase like nickel Cr2O4. So we are interested in this phase, not interested in this. From the mental exercise or physics exercise, we thought that how this phase is developing with that. So we did the Retiefeld analysis. First, low concentration with a single structure and high concentration with the double structure. So friends, I will tell you, if you have any kind of a composite material, this exercise is a very good exercise. You can do the X-ray and you can take the composite of that. So then one can separate out those phases. So we did that also, and I will show you. You have a lattice parameter and C and A. Then for this, the lattice parameter, you can calculate for that phase with the concentration, and then you can see how the phase separation are there. How the chromium oxide phase and the nickel chromium spinel phase. Rhombohedral phase and spinel phase, they are varying. So you can calculate and analyze the composite material in a very simple. This is just a X-ray technique. Many people are using, but they don't put only they are mentioning J peak uski hai, J uski hai, kaisa hai. You can really do the analysis very nicely. Again, the Raman. So you have a low concentration part, you have a high concentration part. Here you can see the peaks of a spinal structure. Here you can see the peaks of the rhombohedral structure. So with this, then IR also giving us the octahedral and tetrahedral structure. Here is only the octahedral structure. Here is a tetrahedral and octahedral. Both are present into the system. And then again, UV visible for those transitions in a single. And here, these are the transitions from the spinal transitions are there. And their band gap is also decreasing up to low concentration, and at high concentration there is no variation, because the phase is different. Now, once we make this order, we cannot study their transparency, so we have to grow a film. So we deposit the thin film of undoped chromium oxide and doped chromium oxide of magnesium, aluminum, nickel using a pulse laser deposition. They are showing very nicely epitaxial film on a sapphire. And then basically the epitaxy, they have a compression along A axis and expansion along C axis. Basically, depending upon the lattice parameter of the sapphire which we have used. Then we look at the epitaxy by phi scan, and they are having a rhombohedral structure and hexagonal threefold symmetry is there. So you can clearly see the threefold symmetry of these films are present. So they are nicely epitaxially oriented grown films we can produce. Then we did some XPS to understand what is the chromium in +3 state, +4 state, and +6 state. And same way, how the oxygen defect states are present into the system, which can give rise to the conductivity. There are various experiments we did using the X-ray photoemission spectroscopy. So those X-ray photoemission spectroscopy are a chromium in case of a magnesium doped thin film, in case of aluminum doped thin film, and then we have studied the magnesium edge as well as the aluminum edge of those, and then nickel again we have studied the nickel peaks, whether nickel is in a +3 state and +2 states are there. So that percentage we have calculated. Now let us come to the final experiment. The aim is a transparency and conductivity. Another experiment, we try to understand the mechanisms of that. Now here you see the transparency in the visible region starting from 400 nanometer to above 800, the transparency is around 70 to 80%. Here you can clearly see, if you put a film on a paper, how nicely you can read behind it in your open eyes. And now you again use the talk plot, and those talk plots will give you the band gap. And you see, as the magnesium is being substituted into the system, the band gap is varying. Now, if you look at the case of aluminium, here the things are reverse. Higher the aluminium substitution, more is the transparency. It means that band gap is increasing and band gap is increasing. Then come to the nickel case. Again, the transparency is good, 70 to 80% or higher than that in a visible range. And the band gap is 3.53, 3.50, 3.48, and above 3 electron volt. So that is the beauty of this experiment. It means these films are transparent. Now, are they conducting or not? So we have measured the resistivity as a function of substituent at room temperature. First, you take a case of magnesium. In case of magnesium, we have reduced the resistivity as a function of substituent to less than I think 3 ohm or 4 ohm centimeter approximately. Whereas in aluminium case, it is insulating and it is going to a 80 kilo ohm centimeter. So that it means that aluminium is not showing a conductivity, whereas magnesium is showing a conductivity. Here in case of a nickel, again, the conductivity is decreasing and it's going even a less than a 1 ohm centimeter with the nickel of 10% or so. Another is the carrier concentration. Now you look at the carrier concentration is increasing up to 10 to the power 19 carriers per centimeter scale. Whereas in case of aluminium, the carrier concentration is decreasing. And in the same way, the Hall mobility is increasing, whereas Hall mobility is decreasing because it's already insulator what Hall ability. Then the case of carrier concentration in case of a nickel is also very high, and the Hall mobility is also increasing to higher value, they even higher than a magnesium. I have tabulated the results in this fashion. So if you look at the pure system, the pure system has a resistivity around 20 ohm centimeter. While substituting the magnesium, you can go up to 3.36 ohm centimeter, which is almost very good. Semiconducting conductivity is good, and metallic type of thing, like conductor, because they are having a semiconducting behavior. Then mobility is a 0.8, very small. In case of aluminium, it is showing a insulator, whereas in case of nickel, in low concentration, the conductivity is reduced to 1.36 ohm centimeter. Hall mobility is reached to the 4, which is almost 5 times even the magnesium case. So it's a good Hall mobility we can consider from at this time. So we can say that we prepare a material which are of p-type conductivity. Secondly, they are having a good Hall mobility. They are good transparent material. Conductivity or resistivity is around 3.36 or 1.36 ohm centimeter. So they can be achievement in this. Now, if you look at the overall table of this, this can hide it, minimize it. You see, Now, here, the last column is the figure of merit, which depends on the transparency, conductivity, Hall mobility, and so. So, the figure of merit clearly tells us that magnesium will have a figure of merit 8.16, and this will be 34.62. That will be giving the quality of the device, if at all. Now, if you compare with the similar kind of material and another kind of material in a literature, what they have achieved so far. Now, we have looked at the literature, many people are got figure of merit, and our work is showing 8.16 and 3.62 in case of nickel, and this, which is almost much higher than only one group like copper aluminum oxide that was having a better than our, but otherwise this new kind of material which we prepared, they are showing a better figure of merit. And these are some publications we have published in an international journal, some peer review conferences or so, and thank you very much for your kind attention. Any question, any doubt, you can ask.
Hello, sir.
Anji.
Sir. I'm Dr. Sandeep from Mumbai.
Yeah.
I just want to ask, can we get supermagnetism in DMS, diluted magnetic semiconductors? Is it possible?
Yeah, we DMS, we have done a lot of work in this direction already in dilute magnetic semiconductor. Even now, in these kind of chromium oxide material, we are working on a dilute magnetic oxide or DMS in these material. And recently, we have published a paper in solid state sciences. In an iron doped system and nickel doped system also. The second paper is coming in this direction.
Okay, sir. Actually, I was asking, in this one hyperthermia point of view, where we require super paramagnetic nanomaterials.
Yeah, super paramagnetic nano. Many people are using a ferrite nanoparticles for like hyperthermia
Yes,
treatment, like drug delivery. So that's a very well-known thing.
Yes, yes. Okay,
because
sir.
ferrite materials are more useful than this DMS material.
Yes, sir. Yes, sir. No, can we substitute this DMS in place of this ferrite or?
DMS has his own many beautiful properties. Why you want to indulge to put that if we have available good material? But you
Yes,
can
sir,
try.
yes.
That's I'm not in discouraging you.
Yes, sir. Yes, sir. Thank you, sir.
because DMS अपने आप में बहुत बढ़िया सब्जेक्ट है भाई, अच्छी एप्लीकेशन, उसके बारे में सोचो, उसको जो ड्रग डिलीवरी में क्यों घुसा रहे?
Correct, sir. Correct.
Well, it's a easy and simple ferrite nanoparticles are working.
Yes, sir. Yes. Thank you, sir.
We did some work long back in that.
Okay, sir.
Any other question, please?
Hello, good morning, sir.
Good morning.
Yeah, sir, my question is related to the iron beam. Of the fabrication of nanostructures by iron beam, and you have very nicely presented and explained everything. My question is simple: that does the iron implantation will change the density of the host material, or it will not affect?
I didn't get your question. Please, can you repeat?
Does the iron implantation
like
change the density of the host material?
Oh, basically
Host material.
it will create stresses in the host material sometime. And if there is a stress, that definitely local density will be changed.
So can we calculate that number?
I have not calculated. If one want to calculate, again, as I have given an example in my second talk, you do the X-ray diffraction and look at because basically these are the small particles taking a microstructure of the host matrix. So you can, if the host matrix is a crystalline like a sapphire or so you can take the X-ray and analyze that, the lattice parameter, and from there you can find out the X-ray density, change in X-ray density in that case. You can calculate, but I have not calculated, frankly speaking, but I can show you the, I have already demonstrated how you can calculate.
Okay.
So ultimately what you have to do, you take a X-ray,
Okay.
and do the Rate-Veld analysis of the multi-phase system. One is your embedded system, another is your host matrix. Then as you are embedding, how the lattice parameter are changing and the unit cell volume is also changing.
Okay, ABC.
So that's why you can, or you can find the strain. If there is a strain, you can calculate, or the volume you can calculate. You can find out the density and everything in that case. Okay.
Hello, sir.
Thank you very much.
Anji,
Thank you,
Anji.
Hello, sir. It's Abu from Guwahati. I met you in Nuclear Science Center. Do you remember me, sir?
Okay.
I was working with Avasti, sir.
Okay.
Sir, I have a small question. Suppose we do the implantation, can we get the nanoparticle on the surface of the substrate?
That I have demonstrated you. Basically, you have to select the dose, you have select the microstructure, you have select the condition of the implantation and the substrate temperature. Okay, so you can definitely, I have demonstrated you can get the embedded nanoparticles under the surface of your very close
just
to the surface.
under the surface. Very close, but not over the surface, no, sir?
Over the surface, I have given you a second demonstration in the same lecture, same part of my lecture.
Yeah, exercise, high radiation.
So that's what.
High energy.
So both the technique I have showed you.
Okay, thank you, sir.
Okay.
How are you, sir? How are you now?
I'm fine. I am fit and fine.
Okay, sir. It's been a long time.
Yeah. Any other question, please?
Hello. Am I audible, sir?
Yeah.
Yeah, sir. Good morning, sir. I'm Dr. Somodita Sutradhar from Amit University, Kolkata. So,
Okay.
sir, your lecture was very nice and it helps us to understand the electrical property of dope system. Now, I would like to ask you that, can you put some light on the modulation of dielectric property of this kind of doped nanosystem?
Yes, one can study the dielectric properties also in that case, but I have not done that. If you have basically you can measure the dielectric property using a two way. One is the DLTS technique. Another is a simple dielectric LCR meter or impedance analyzer of that.
Right.
So one can find out those kind of parameters in that. But I doubt that can we isolate the dielectric behavior of my host material and the dielectric behavior of my embedded material. वो separate out करने के लिए आपको थोड़ा यत्न करना पड़ेगा. You have to do first your host material, then embedded material, then again, basically the dielectric properties are very much coupled with the stresses generated into the material. So while embedding the nanoparticle, if you have generate the stress in your host matrix, its dielectric behavior will also change.
Okay.
That basically it's a complex system. I have not measured. I'm just because from my experience I am guiding you.
Definitely.
One has to do so many experiments to find out the real value of that.
Okay.
That's why there's a complications in the dielectric properties.
All right. Okay. Thank you, sir. Thank you very much.
Okay, sir. Any other?
Any other question from participants? Thank you, sir, for giving valuable knowledge on the topic nano.
आवाज नहीं है. Hello.
Thank you, sir. Thank you, sir, for giving valuable knowledge on the topic nanomaterials, and thank you for sparing valuable time for us, sir. Thank you.
Okay.